thank the participant, the organizers for inviting me to present some of our results. It will be less about generation, energy harvesting, detectors, so maybe a bit out of a character of this workshop. It will be more about computing method, cryptography, signal processing, and so on. Okay, so the outline of my talk is the following. I will briefly discuss some interesting stuff regarding novel computing methods utilizing magnetic systems. Mainly, I will talk about Ising machines and a lot about probabilistic computing. I will not talk today about neuromorphic computing. That's another big section we can talk about and can use magnetic systems for, but I have limited time, and after the lunch there will be a big talk about neuromorphic computing, so I hope that part will be covered there. Okay, so what is this all about? For people that know magnetism, they know what is Ising Hamiltonian and how it describes our magnetic systems. It's model Hamiltonian. It doesn't take into account everything, but it's quite well known. And on the other, let's say, part of the spectrum, that's mathematicians. And they are dealing with NP problems, non-deterministic polynomial problems. And at the first glance, nothing can connect these two things, because Ising, that's magnets are magnets and mathematics is mathematics. But mathematicians have proven some very interesting theorems and some interesting results that I will not show here. I will spare you of this, but the result is the following. Any NP problem can be considered as a problem of minimizing of energy state of some Ising Hamiltonian, and vice versa. For each Ising Hamiltonian, there is an NP problem which it solves. Moreover, you can go even further, and at the bottom of the screen you see that basically the first term, if you're familiar with neural networks, the first term reminds you of offset of a neuron, and the second term reminds you of the sum of the inputs into one neuron. So basically, as I said, the answer to a particular optimization question becomes the equivalent of searching for the lowest energy state of the Ising model, of the Ising Hamiltonian. So this is the key idea that lies in so-called Ising machines. So I will tell briefly about quite novel, it's 2022 results, a spin wave Ising machine using spin Hall oscillators. This is a result by Sweden scientific group. So as you can see, they created four nano oscillators, and from the oscillation theory, it's quite known fact, and you already heard today that if we apply external force, then this system will be synchronized on the frequency of this external force. Nothing interesting here, but and the phases of all of the synchronized oscillators will be the same. As you see, this clockwise rotation on the upper panel. But if you take the force over the double the frequency, then the oscillator can have some freedom. It synchronizes, not a question, but it can synchronize with two different phases, differ by pi, clockwise or counterclockwise in our case. So basically we arrive to the some systems that can have two distinct states with phase going clockwise or counterclockwise, and basically that is all we need to introduce some simplest Ising machine, because as you know, in Ising, in Ising machines, this SESG operators are basically spin operators. They can be up or down, so they have two distinct states. And here we have same idea. We have oscillators synchronized by external signal, and they have two distinct states, but regarding phase. So they took this idea, they fabricated this array, it's 2x2 array of spin-Hall oscillators, and they conducted some micromagnetic modeling, and they conducted phase-resolved Brillouin scattering, and they indeed show that we can by changing magnetic field, we can indeed influence the synchronization state of the oscillators. As you see, it can be a checkboard-like story when some are going clockwise, some counterclockwise. It can be majority, all four going counterclockwise, and so on. And basically, every this spin orientation is answer to some optimization problem. However, it's not that simple because we need to have a way to modify inter-oscillator coupling. This can be done by applying electrical field, by applying voltage anisotropy, but in this work it was not done. So, but it's only the first step, and it's very promising. So basically, this spin-Hall oscillator array, they can be scaled. They can be 5 by 5, 10 by 10, easily, and they can be a first building block of the Ising machine. Okay, now let's talk about probabilistic computing. So let's say we have an element that, let's say we have a nanomagnet, north-south, as you see, with north and south pole, that can fluctuate in time, go up or down, up or down. And we are trying to create a binary multiplication gate using this stochastic element. If elements doesn't communicate with each other, have no connection with each other, each state of these three bits is equally probable. You have 2 by 2 by 2 states, as you see on this diagram. AB codes input and C codes output, and you have 8 probabilities, and all these probabilities are equal, 12.5%. Nothing astonishing here. But if we cleverly engineer communication between the bits, then not all the states become probable, and only the states that corresponds to the true-false table of this multiplication are present in the system. As you see, if the AB is 0, then the C will be also 0. So, okay, this seems interesting, but not yet astonishing, because okay, another gate that we've seen a lot. The strength of probabilistic computing lies in the following fact: they can be reversed. What I am speaking about. Let's say we locked our input to 0, 0. A bit is 0, B bit is 0. Then the output bit C will be also 0, and 100% of the time our system will be in this state, as you see on the left panel. Okay, good. But what we will do the following: we will freeze the output. We will lock output to the 0. Then the system, let's say, knows that there are 3 possibilities of input to satisfy the output, and between these 3 possibilities, system fluctuates with, let's say, 33.3 in ideal world, 33.3 probability between these three states. And this is very powerful stuff. We can solve inverse problems. Why it's important? I will tell a bit later. Again, what we need for this system? We need some stuff called a p-bit. It's quite simple idea. It's a system, some systems that can be in 1 or -1 state, and by some external signal, we can switch this probability, as you see. Without, let's say, external signal, it's 50% of the time is 1, 50% of the time is -1. With large, let's say, negative current, it can be current, it can be voltage. I will tell you more about it later. So negative current, it's almost every time in the -1 state. Positive current, it's almost all the time in the 1 state. So basically, this is the key element of probabilistic logic, and we need such an element to fabricate these schemes. And it can be done with magnetic tunnel junction. There were a lot of talks already about magnetic tunnel junction. We have fixed layer and we have a free layer. And basically, in ideal world, we don't want it to be stochastic. We want it to be, let's say, magnetic memory. Yeah, we can code depending on the top layer, antiferromagnet or ferromagnetic state. We can code some information. Yes, but let's say we can apply some voltage. The energy gap between these two states lowers, and the system become unstable. And as you see on this diagram, there is some region of bias voltages when this magnetic tunnel junction due to thermal noise become unstable and fluctuates between two states. And that's basically what we need. We have magnetic element that can be used as a p-bit, and it can be controlled by voltage. Great. A bit intermediate about integer factorization. Even a 5/5 grader with a calculator can quite fast multiply two numbers. But if you give him the same calculator and give him some number and ask him to divide, to factorize this number into prime multiplans, it doesn't take seconds. It can take minutes, hours, depending on how large number you choose. As a sample task, you can try to factorize 667 while I speak my presentation. So, and this idea that we have some algorithm that fast forward and slow backward is a key idea of modern cryptography and modern RCA algorithm. The day we will find the way to speed up the factorization process will be the day when the model cryptography dies. So, with all mentioned above, in 2019 there was a great work published in Nature where magnetic tunnel junction were used exactly for that. They were used to factorize numbers. As you see, they use different number of bits, and in the simplest case, they have locked output to the number of 35, and the output was 7 and 5 and 5 and 7. Some degeneracy, obviously, but system indeed works. So system indeed shows that it can factorize numbers, and it can factorize it using magnetic elements. Because you can use CMOS elements, CMOS elements. There is stochastic generators using CMOS, but as you see, we are talking about thousands of transistors, and we are talking about much higher energy consumption. Okay, so this was a magnetic tunnel junction. Now let's move to some original results of our scientific group, and it's using such, well, in 2019 when I was giving the first talk, I was saying it was novel. Now in 2023, it's still, I believe it's still novel, but it hasn't been yet fabricated. However, what is the system? This is quite simple. It's platinum, heavy metal, and on top of it, antiferromagnetic. However, not any antiferromagnet, but antiferromagnet with easy anisotropy. When we apply DC current to the platinum, we have spin Hall effect acting on antiferromagnet, and due to this anisotropy field, that is very important, Néel vector rotation, as you can see on the second graph, is modulated by some terahertz frequency. This terahertz frequency can be detected by inverse spin Hall effect. As a result, we have DC input with the terahertz output. It's very promising system, and as you can see here some results. So not that large currents are needed to obtain sub-terahertz or even terahertz frequencies. And the question that we asked was, can the system operate in a stochastic regime? And the answer is yes, indeed. By moving from DC input to the AC input, we can, and by choosing frequency of the our signal, we can indeed make antiferromagnetic spin Hall oscillator operate in a stochastic regime. This way, you can consider it's like a random amplitude modulator. We apply some sinusoidal signal in the input, and as a result, we have output signal with randomly modulated amplitude and close to the input frequency. So, and then the next question is, okay, great, we have terahertz operating stochastic system. Can we somehow create a bit using it? And the answer is again, yes. This is just showing how the signal looks. It's indeed stochastic. So there, mathematically, you can do a lot of stuff to convert one signal to another. We propose so-called Markov signal converter. Basically, we consider as our this stochastic signal as a driving signal for another simple Markov system. It has two states, 1 and -1, and depending on the detected amplitude of this stochastic signal, it either remains in this state or it switches. Quite simple. So you need to set two amplitudes, and here you go. Principal scheme of p-bit, you can see it below. So we need the first spin Hall oscillator to produce this gigahertz harmonic signal to drive the second one spin Hall oscillator. After that, it goes to this signal converter, and as a result, you arrive to the p-bit-like signal. And there is some modeling. You can indeed, by choosing the amplitudes, controlling amplitudes, arrive to the 50-50% probability, or the system will be in one state or another state, depending on amplitude you choose. And basically, this is nice and all, but I think this is the key slide of our results, because we can compare magnetic tunnel junction, it's to the right, and our spin Hall oscillator to the left, and just look at the time scales, microseconds versus picoseconds. It's 6 order of magnitude faster. With such fast probabilistic logic, it's basically a revolutionary. It can revolutionize everything Indeed, magnetic tunnel junctions are already working, and they are already fabricated. Antiferromagnetic spin-hole oscillators are not yet fabricated, but we believe it will be soon be done. So, as a conclusions, probabilistic computing is a nice alternative to the quantum computing, which everyone is talking about, and the key element of the probabilistic computing, pi bit, can be created using antiferromagnetic spin-hole oscillators, and it operates in sub-terahertz frequency comparing to the gigahertz or megahertz frequency of the magnetic tunnel junction. Thank you.